Uh, okay, first acknowledge there's a lot of people working on this project, and so most of the figures in here are my figures, but I think most of this data, the various aspects related to like earthquake seismology, are going to be handed off to other people as they get interested in the data, makes it back here from Alaska to Seattle. In particular, we have some collaborators outside of UW, also Eva Golos at the University of Wisconsin, who's going to be doing some interesting tomography stuff. And Casey Adderhold at EarthScope, who's been super helpful because she's actually a resident of Homer, Alaska, which is where our interrogator is located. So just, oops, now I can't send you slides. Let's see. So just some really broad background, of course, an overview of the Alaska subduction zone. So I'm going to step away from the computer, so hopefully I'm still audible. Homer, Alaska is here, which is where we deployed our gas interrogator. This is the Cook Inlet. It's kind of in the armpit of the Alaska subduction zone. You have the Pacific Plate basically normally incident up here. You have this purple outlined big rectangle that's the Yakutat terrain, which is this kind of weird, ultra thick, but potentially still mafic oceanic crust microplate, which has been subducting for the last 10 to 20 million years under the further northernmost part of the North American plate here. And it developed this kind of odd flat slab subduction where there's a gap in seismicity. There's also weird pieces of other plates, like indicated with the Wrangell slab, and kind of odd distributed seismicity. But the seismicity is a lot that we're interested in is mostly to the west of that, where we just have much more normal subduction. And so you can see that we're in this kind of transition range here, where we go from having flatter subduction to the north and more ordinary subduction to the south. The other thing that's notable is, of course, this volcanic arc and the fact that there have been a number of very large earthquakes in historical time, most famously the 1964 one, which ruptured very close to our array. That's the top. People see this mouse? That's maybe a better way to do this. Yeah, the mouse is better. The top up here, here's our array for reference. So there's a couple potential targets scientifically. Obviously, if we can just learn more about the structure and seismicity patterns in the Alaska subduction zone, that'll be informative because the network here is so sparse, in particular because there's so much offshore area between the trench and the coast. There's very little coverage, both geodetically and seismographically. And so here, for example, is a paper by Aaron Weck that shows a couple slow slip events that have been identified variously, both one directly under our array and one to the north near Anchorage. There's also been tremor that's been noted on shore, or rather at 50 kilometers or so depth under the onshore segment. There hasn't been tremor noted offshore around Cook Inlet. Similarly, there's been a low frequency earthquakes potentially associated with a slow slip event or tremor or both under Kodiak Island, which is further to the south. So there's kind of a potential gap in what's been mapped, both in terms of tremor and in slow slip, right around where our array is located. There's, of course, volcanism, arc volcanism all along the north side of the Cook Inlet. And the most interesting volcano for us is Augustine volcano. This most recently erupted in 2006, and there was lots and lots of seismicity, both before, during, and after, in kind of a swarm-like fashion, as you can see here on the time in years versus depth, basically at the surface on this little island. And one of our cables runs very, very close, within about 25 kilometers of this island. So theoretically, at least we can record some of the seismicity and characterize what's going on. Another thing is environmental. There's very, very complicated circulation patterns in the Cook Inlet. It's also what's called a macrotidal environment, meaning that the run-up of the tide is extraordinarily large. And so there's large tidal currents in addition to the mean circulation shown here. Another complicated aspect is that there's sea ice because you have freshwater flow out from all of these river valleys. In the north of the Cook Inlet, you have basically a freshwater plume that propagates down into the Cook Inlet and allows the freezing of the shallow water in the winter. And so you can see here, actually, there's quite a lot of ice north of Kenai. This is the mean annual sea ice concentration for March. And what's shown here in pink is the 70% surface concentration. And what's shown here with the hatching is that it's typically greater than 30 centimeters thickness. So there's actually quite a lot of ice up there. This is also reflected in the ambient seismic field. Not only if you look at a spectrogram of the seismic observations from around this whole area of the Kenai Peninsula, can you see that there's actually tidal modulation of the microseism amplitude as these strong currents are affecting the wave condition? But you can see gigantic seasonal variation, which is correlated with this sea ice. If you look here around, your typical band of 7 to 14 seconds in the ordinary kind of regional microseism part of the spectrum, for the station CAPN, if I remember correctly, is somewhere around here. Maybe it's north of Kenai. But it's right on the coast of the Cook Inlet. You can see that, of course, the regional microseisms are stronger in the winter because there's large winter storms driving large ocean waves on the Pacific coast. And while those regional microseisms are muted in summer, you can actually see there's a new distinct microseism peak, which greatly exceeds the typical high noise threshold, which is representative of local microseism. Like people see lake microseisms around the Great Lakes. This is kind of 1 Hertz microseism is characteristic of the wave conditions locally in Cook Inlet. And you can see that in the winter, it's suppressed most of the time because of the sea ice. So there's potentially some information that we can extract from the seismic field about the ocean and ice dynamics. So this map, nicely made by Cheap and Cheap, so I'll use the mouse, shows the cables that we have access to. There's 3 of them. One of them shown here in gray, KKFLN, that's the Kodiak Kenai fiber link north side, goes up from Kenai here in the north down to Homer, and it all runs offshore. These cables are buried and they're telecom cables. So while they are armored, meaning that they have metal components, they're relatively stiff and elastic. They're not super thick. They don't have large conductors like power cables do in them. The southern end of that cable shown here in blue connects then from Homer over about 320 kilometers down to Kodiak Island. And then we have access to another cable called Terra Southwest, which runs east-west from Homer over to Williamsport, which is a tiny village in Iliamna Bay, which has a road over the mountains into Port Ellsworth and some of the other hunting and native communities that are on the other side. And so what we've been doing is since June, we have a setup with a DAS interrogator, one of these Centella Onyx units owned by the UW Fiber Lab. And it's able to connect to 2 different fibers. One fiber that we're using currently is the KKFLS fiber in blue. The other fiber that we're currently using is the Terra Southwest fiber in red. And we will hopefully then record over the winter when we have these interesting sea ice conditions on this north fiber, but we haven't been able to do that yet. We also have it set up with a server in the field that has 4 drives of local storage, as you can see, and also a pretty good set of CPU cores, so that we can run remote jobs without having to bring the data back, because the data rate that we can transfer over the internet between Homer, Alaska, which is a pretty small town, and Seattle is not high enough to bring back the data in real time. And so, of course, the third thing that we have then is a giant NAS, a giant storage unit with lots of RAID redundant data storage that'll last us theoretically up to 2 years at the current rate that we're recording data. So we started doing that in early June. And the first job that I had is to basically look at the data and see where the heck our data that we record in terms of optical distance, i.e. the travel time of a DAS laser pulse through the fiber, how does that actually relate to physical distance? And so ordinarily onshore, we could go around, we could tap, we could correlate the locations where we hit the ground with a sledgehammer with where we see that sort of signal in our data. Offshore, this is a little bit more difficult because we really only have one good datum, and that datum is the coast. It's where we see the transition from ocean waves to non-ocean waves. And unless we go out there with like a marine seismic survey, it's going to be hard to get other points of reference. But I'll show what I can try to do here. And so we have from NOAA, there's an open database of cable locations that are pretty precise. We can point out the location which is closest to the high tide mark. And then we can look at a spectrogram of our data, and we see actually direct ocean wave loading, which I'll come back and talk about in a few minutes, in the kind of 10 seconds to a few hertz band. And we can see that over the course of several days, this is tidally modulated with 12-hour period. We can also see that there's a really complicated beating between the diurnal and semi-diurnal tides, that as you go further out, you can see that the wave run-up is less at 24-hour period. And what this basically represents is the high limit of where the waves actually run up on the beach. Because it's in this weird macrotidal environment, the waves actually run up and down as much as 500 or 600 meters in places horizontally. So the tide draws way in and it draws way out. And so what we're looking at here, for example, in the red, is a time when the waves are on top of the cable at this one location. Then we're looking at the blue is the time when the waves are not on top of the cable at this one location. It's just very quiet and open air. And so we can, if we go up along the cable, we can find the point where there's just a teeny bit of wave energy every once in a while at the strongest tide. And that point we can clearly identify as the high tide line, because it's pretty much a cliff at the beach here. And so, we can't go any further than that. And then we can extrapolate the cable locations out from there by interpolating between the survey points that are given by NOAA. And what we end up with is this, that basically with our single interrogator that is looking at 2 fibers simultaneously, we can see out to about 82 kilometers in each fiber. And for the Terra Southwest fiber, this takes us about 2/3 of the way across the bay and about 30 or 40 kilometers away to the closest point from St. Augustine volcano. This fiber, which is the one shown here in red, is very shallow. It's almost exclusively all around 50 meters water depth, which means there's a lot of ocean wave energy kind of overprinting our seismic data. It also crosses here, this is somewhere around the 50-kilometer ISO depth mark on the slab, and then the 60-kilometer ISO depth mark is more or less in the middle / other side of Cook Inlet. And so it's kind of centered over that area, which is just below the flat slab part to the north, and kind of at the transition from potentially being locked to the SSEs and tremor deeper, below 50 kilometers or 60 kilometers or so. The other cable kind of goes into this deep channel. This bay here is called Kachemak Bay, and it also is totally drained out, well, not quite totally, but mostly drained out tidally because the currents are so large. And it has this sort of channel that it's been carved out by these extreme currents that are pulling in all so much water in and out. And so the KKLFS cable basically goes down the side of this sort of cliff into this tidal channel and then travels down that channel and actually makes it a pretty good way down to about 200 meters depth out here. And so we maybe, if the SNR is good enough, can actually see some interesting signals from the Pacific at the end of this cable, open ocean swell, maybe there will be whale calls. Still lots of work to do, obviously. So how good is this channel location? One thing we can immediately see are ocean waves. The ocean waves, just for demonstration here, are horizontally propagating. They have pressure which decays exponentially with depth, and so they load the seafloor in shallow water, and we can basically observe the quasi-static deformation of the seafloor on our cables in the kind of ballpark of 10 seconds, which is where the ocean wave band is centered. And this gives us a nice kind of test to see whether the bends in the cable that are given to us by the NOAA geometry actually correspond to the bends in the cable as we're measuring it at the right distance where we think they are. And it turns out that this works more or less, that we're lined up within a kilometer pretty much everywhere of where these kind of tie points where the bends in the cable are, because they show very clear changes in ocean wave directivity. So you can see, for example, this is raw ocean wave data over 2 minutes and over 2 kilometers horizontally. And there's a sudden sharp like chevron, and that correlates with I'll ignore the cross correlations for now. That's probably take too long to explain, but that correlates with this bend from A on the left to B on the right. And what we're probably seeing is that the waves are traveling about 30 degrees oblique to the cable. And so when we go around this relatively gentle bend, one of the directions aligns up with the cable and becomes very strong. The other direction is nearly normally incident, and therefore it disappears. And so this is just a small bend, but it tells us that it lined up correctly when we compare one bend here, right? You can see that this chevron and the corner and the actual cable geometry are lined up. This one is not well lined up. And so we know that there's at least a few hundred meters of uncertainty in some parts of the cable, but the simple extrapolation procedure is maybe a bit dubious. And so it's definitely something to refine in the future. Okay, but so the main star of the show with this data is earthquakes. We saw on the map that Sheban had earlier, that was just 1 month of earthquakes that are in the Alaska Earthquake Center catalog. This is 1 day of earthquakes that are detectable by our DAS array. We've set up this automated script that goes through the Alaska Earthquake catalog every day, pulls events above some simple ground motion model that should be detectable on our array, creates some nice plots, calculates some statistics about what was recorded to make sure that the array is still running, and then sends it to us by email every day just so we can see what's going on. And so you can get an idea here that this is over just 120 kilometers connecting the 2 cables together. that we can have continuous travel time information from as many as a dozen earthquakes every day. And so over the course of the full year that we're planning to run this experiment, we're going to have quite a large data set that can be used for things like regional tomography, earthquake location studies, etc. I just want to now zoom into some of these and show off how beautiful this data is. Unfortunately, the blue color that's in this is like black on the screen, and so it's a little bit hard to read some of the details here, but I'll do my best. So the first thing is just here. This is a local slab interface event. I forgot to include the map, but it is directly under the east-west cable on the far end. So if it's about here at basically 55 kilometers deep on the slab interface. And so just taking a simple like ISP 91 deep velocity model, predicting the synthetic travel times, and comparing them here in yellow and orange for the P wave and the S wave over the full 164 kilometers of cable that we have. This is the east-west segment. This is the north-south segment. You can see first that there's some ocean wave-related noise before the earthquake occurs. The next thing you can see is the P wave, and there's quite large for this earthquake, which is basically directly under. There's already a 1 second, 1.5 second residual on the P wave. So there's plenty of room for making a nice 3D velocity model here. You can see the hint of this here, that there's some sort of kind of diffuse secondary phase in the P coda that you'll see much more strongly on deep events. And then we have the S wave, which is much stronger and easier to see. This is because the DAS cable is a horizontal cable, and it's also measuring strain. And so it's primarily sensitive particularly for an earthquake directly under the cable to the horizontally polarized or shear ground motions. And you can see if we zoom in, I take away the synthetic travel time, that this S wave is really beautifully coherent. And we can actually see a polarity flip here. This is, if we go back to this map, right around here, the bend on this cable, and that's just not related at all to the focal mechanism of the event. It's simply because we're measuring strain, the gradient of ground motion along two angles, one angle which is about positive 30 degrees from the cable axis, from the wave front direction coming away from the from the epicenter, and one which is about negative 30 degrees away. So the direction, the sign of the gradient flips going around that bend in the cable. For some other events, we can see even more beautiful, coherent, complicated things going on in the S wave. I'm not sure any of this is really visible, so I won't belabor it. This is a shallow event also nearby. This one, you can actually see some of the P wave is more coherent. What is maybe most exciting for this, I don't know, it depends on what you find most exciting, is that we can see really, 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 really tiny, super deep earthquakes, even though we can't see really tiny, shallow earthquakes. It's not exactly clear to me why this is, but here's a magnitude 1.8 that's 156 kilometers deep, and also about 80 kilometers north of the closest point on the array. And we can see beautifully the S wave. And actually, the travel time residual for some of these deep events is much lower than the travel time residual for many of the shallow events, which is interesting. Don't know what to say about that other than that they exist. For the larger deep events where we can see the P wave, here's, for example, a 3.7 in more or less the exact same location as the previous event, which you can tell by comparing the travel time curves. The secondary phase that I was describing is much more obvious. You can see that there's a emergent part over here, kind of more diffuse over here. Yeah, unfortunately, that is much, much clearer on my screen and not on the projector, so I apologize. But you can see that there's kind of like this increase in energy, right? And we don't know what this is yet, but it will definitely contain structural information. It could be a PS conversion. It could even be like PMP within the subducting slab that then comes back up. The fact that it has higher amplitude than the primary P suggests it's probably a converted phase, though, given what I said before about horizontal particle motion and strain. The biggest event we've recorded so far is the magnitude 7.2 Sandpoint event that occurred earlier this year. If we go way back, probably should have pointed this out earlier. This event is down here. So it's like 800 kilometers away. It's nearly Thales size metric by formal definition. And obviously, there's a lot to be done in terms of improving regional velocity model. This is greater than 10 seconds travel time as usual with a P wave. This is just very high frequency filter. But as we move to low frequencies, we can see things that are more and more coherent. The other thing to note is, again, this is super washed out here, but if you zoom in with your eyeballs, you can see that there's like crossing X's, right? Like chevrons intersecting with each other all throughout the coda. So it looks like there's just this giant mess. But even at these very high frequencies, we're seeing near surface scattered waves basically diffracting away from local scatterers in the surface here. And that's dominating the coda of these events. So it is actually very coherent at these high frequencies. It just looks terrible on the screen. As we go to lower frequencies, this is now 1 to 10 seconds. We can start to see some really exciting stuff. So this, I'll use the mouse again, sorry. This is the first P motion, the little red thing here. And you can see that its move out is consistent with the prediction. What's before it is vibration of the interrogator, creating this quote unquote common mode noise, just artifact. And then you can see that, interestingly, we have this really beautiful coherent 1 to 10 seconds coda, but that the apparent velocity is much slower than the P waves move out. And so most of this is probably, once we move up into here, converted waves, like surface waves. And we have some really good evidence of that if you look over here, because as you can expect, we have the earthquake, which is to the west, and Cook Inlet is more or less oriented northeast, southwest. And so most of the energy from the P coda is coming in directly along the same path as the P wave, just straight in without having to interact with any, mountain ranges or whatever. No scattering off of basin edges. But clearly some of the energy has hit, I don't know if it's Kodiak Island or the lower edge of the Kenai Peninsula on the other side of the bay from Homer, but it's actually propagating back in the other direction. And so before the S wave even arrives, there's this very complicated pattern of surface waves that are basically crossing Cook Inlet from 2 different directions due to basin scattering or edge focusing or whatever you want to model it as. We haven't attempted to model it yet. But it actually is a dominant horizontal ground motion during that period. And then finally, the S wave shows up very clearly. Again, you can see that the travel time move out matches the theoretical model pretty well. And then it's followed by slower surface waves, which are probably the direct surface wave phases. And if we go even lower frequency, 10 to 100 seconds, this becomes very obvious. First of all, there's some sort of very interesting 50-second period pulse that occurs in the P coda, which appears to be about 10 seconds or 20 seconds too late to be actually coincident. It's not part of the direct P, or if it is, it's some, I'm confused by this because it's there's nothing correlated with this phase in the higher frequency part of the coda. I don't think there should be a strong W phase for this birthday, but I'm not sure. This wasn't like right at the trench. This was a pretty, it was like, I'm not sure. But I haven't compared this with the local size mountain, so I don't know if this could also be, this also could be like, it's not common mode noise. You can definitely see that there's move out on that side, but interestingly, if you look on this side, the apparent move out is faster than the direct P. So it's something very strange. I have no hypotheses. Okay, then you see the low frequency part of the S wave. And then what's very cool is you can actually see the difference in polarization between the Rayleigh and the Love waves as they come through. So for this first really low frequency 20 to 50 second surface wave pulse here, you have go from red to blue as you go around the 90-degree bend in the cable geometry. So you have a polarity flip. But as you have these slightly higher frequency, presumably Rayleigh waves that come later, you can see that this is red to red, blue to blue, red to red, blue to blue. So there's no polarity flip. And so these are at least 90 degrees different in terms of their polarization, which is obviously what we expect for these long period regional surface waves from big earthquake like this, but it is kind of cool to see it. So somebody will have a lot of fun looking at that earthquake who actually has the appropriate modeling skills, which is not me. But it's a beautiful part of the data we've collected. A big part of the data that we were hoping to collect is the ambient noise, because I showed you that there's that correlation with this high frequency 1 Hertz peak between the ocean wave conditions and what's recorded on the seismometer. Interestingly, we don't really see this. We're dominated instead by the ocean waves across this sort of band. So what I've plotted up here is the NOAA wave buoy in Lower Cook Inlet, which shows between about 10 seconds and a few hertz, these really short period wind waves generated by the local meteorological conditions in Cook Inlet over the course of a month. Below that, we have the vertical spectrum of particle velocity, which shows these pulses of microseism energy in this high frequency band that are temporally correlated with local high wind conditions. And you can see that on this plot, that if you look at the ignore the DAS, that's black. If you look at the buoy in blue and the seismometer at double frequency in red, these are double frequency microseisms. You can see that especially as you go to higher frequencies, there's a pretty good temporal correlation between high waves and high microseism amplitude. But interesting, if you look at the DAS, this looks, it's a little bit messy. You'll see a clear comparison later, but this looks a lot more like the Cook Inlet buoy than it looks like the Homer seismometer, right? We don't see any of these high frequency microseism pulses. And if you look at the same correlation between the DAS in blue and the buoy in black here at the same frequency, they're pretty much 1-to-1, at least at lower frequencies. So how are we going to get structure? One of the things I've started to do instead, because we don't have good ambient noise, at least from the first few months of data to look at structure, is look at earthquake coda waves. We saw how there were all those beautiful chevrons related to scattering from body wave energy into surface wave energy in the earthquake coda. And so we can cross-correlate those just like we cross-correlate seismic ambient noise, get an estimate of the Green's function, measure dispersion, and hopefully do some inversion. So this is work that's in progress. But so now I'll move away from seismology and move into oceanography, which is something that is proven very fruitful so far. And one of the reasons for that is because we have ground truth, which has been a little bit stymieing in previous studies, that there is very little particular ground truth oceanographic data anywhere near our cables, even though there are these beautiful oceanographic signals in the DAS data. Fortunately, we have this buoy. This is a photo of the actual buoy with the volcano in the background, managed by Scripps, but paid for by NOAA. In blue with triangle, and it's pretty much exactly 500 meters away from the closest point on the Terra Southwest cable, the one that runs east-west across the middle of the inlet. And so it gives us all this beautiful information about the wave spectra and time. It gives us, these higher order statistics that are commonly used in oceanography and coastal engineering. And it very conveniently also has an ADCP, an acoustic Doppler current profiler mounted on the bottom, which means that it can actually measure the flow speed. And it gives us this time series with the surface current, which is perfectly enormous. This is the east-west flow here in black. It's as much as about 1.5 meters in amplitude at certain times. Sorry, meter per second in amplitude at certain times. So if we just look at the data on an individual channel, you can see that it's got this oscillation around 10 seconds. And if you look at the data in space, you can see that it has these beautifully moving out, strongly dispersive wave groups. You can see that, of course, that the group energy here is moving slower than the phase energy, which is moving faster. And these have a characteristic velocity of about 10 meters per second. As you can see, this is 5 minutes. Sorry, this is 3 minutes and 600 meters. And if we look at the spectrum of this, ignore the bottom one, the variance among channels doesn't really matter. But if you look at the spectrum, you can see that, first of all, there's over the course of, again, 1 month here horizontally, that we mostly see between about 0.2 hertz all the way down to 0.02 hertz. The strong energy in 2 groups. We have these 10-second or so waves, which are what you're dominantly seeing here. And then there's also lower frequency modulation. So these high frequency waves around 10 seconds are, again, representative of local wind conditions called wind waves. The lower frequency waves are called swell, and they're propagating in from distant storms, presumably in the Pacific, and then kind of refractively getting trapped in the Cook Inlet. But they're much weaker here than you would see on an open ocean buoy. And also you can note that these are dispersive. That's indicative of how far away they are, because just like seismic waves, ocean surface gravity waves are strongly dispersive. The further you away you are from a source of ocean waves, like a distant storm, the more you can see this linear dispersive trend, because the high frequency energy arrives long after, in terms of weeks after, sometimes, the low frequency fast energy. Sorry. We need a stick. I don't know. I can't. Wait, but I need a linear pointer. Can you see this? It's heavily tightly modulated. No, but it's not super obvious. But it's actually more obvious if you look at the buoy record of the same thing. These low frequency motions are so weak at the surface that they're barely recorded by the buoy, but you can see the same trend here, right? This linear dispersion from low to high frequency over the scale of like a week or a few days. So first thing we want to do now that we know that we can see these beautiful ocean waves is compare them with the buoy, since we have this in situ, and see, can we estimate these same sort of ocean wave statistics? And what I did initially is basically just take a naive spectral ratio. So this is the spectral ratio between the buoy spectrum and the seafloor spectrum, the closest channel, just 500 meters away, every hour for a month. And if we take the mean, we can then basically convert our DAS data into buoy data and see, I'm going to skip over that, and see if we can estimate wave statistics. And so this is the time invariant empirical transfer function corrected to DAS data. So now in units of sea surface displacement. And this is the actual buoy data. And you can see that below about 0.5 hertz, where you start to have weird things happening on the DAS data, probably representative of other signals like acoustic or seismic signals that are ephemeral. These look surprisingly very, very similar. And happily, we can calculate the same sort of statistics pretty reliably. So for example, here we have wave period defined various ways. Ignore the black lines. This is what NPPC reports. These are different sort of time averaging that I wasn't able to reproduce. But the estimate in red is my estimate from the raw buoy data, and estimate in blue is my estimate from the DAS data. And while it's not super great at estimating the average wave period, you can see that there's pretty large disagreements in some periods due to the fact that the DAS is at depth. The low, really, really short wavelength, high frequency ocean waves are attenuated and we just never see them. And so averaging the periods across the spectrum is never going to be robustly one-to-one with the surface data. The wave height, which we care about, compares very, very favorably. So we can basically estimate using a one-time estimate of the empirical transfer function between the sea surface and the sea floor, how high the ocean waves are from the DAS data. And you can see that here, there's a significant wave height HS between the DAS and the buoy. And while it diverges a bit at the higher end, it's pretty much one-to-one. Interestingly, there does seem to be some directional dependency. It's not surprising. So there's no tidal effect. This is the M2 tidal phase versus the estimated wave period residuals between the DAS and the buoy. The estimates the wave height residuals between the DAS and the buoy. So even though we have these plus or minus 1 meter per second currents, they don't seem to affect our ability to measure anything, which is great, because it means we can do things like study the wave current interaction, study the currents, because they're not biasing our results. The other thing is that we have the ability to look in terms of the different directions the waves are propagating from. And here we do see some systematic residuals, in particular when the waves are propagating more or less from the southeast, we tend to overestimate their amplitude, whereas when the waves are propagating from 90 degrees over towards the southwest, we can underestimate their amplitude, just using this simple model. So there's room for further work that I'm doing on trying to correct basically for the directional sensitivity differences between the buoy at the surface and the DAS cable at the bottom. One way we can do this is by taking a spatial spectrum. So we have coherent channels lined up next to each other in space at uniform distribution. So we can take a Fourier transform in space as well as a Fourier transform in time and get this frequency wave number domain representation where a line like this would be a line of constant phase velocity. So we can then superimpose the ocean wave dispersion relation for a given water depth, which is analytically known. We see that, of course, the wave energy sort of follows it. And then as we step up along these black lines, each of which indicates 20 degrees, we can imagine the apparent phase velocity being slightly faster for a plane wave propagating oblique to the cable. Obliquely incident apparent slightly lower wave number or slightly higher phase velocity. And so this kind of thickness of this blob at any given frequency is telling us what the directional distribution of the wave energy is. So we can just do then a coordinate transformation using those dashed lines to get the distribution of energy versus azimuth. And And you can see that this distinct swell group, which is a peak at some angle oblique to the cable, and then the wind wave ocean wave group, which is separate and has a peak direction closer to the azimuth of the cable. So this is ongoing work to do this systematically. And the thing I'm very excited to do next with this is that these wave buoys are actually vector sensors, that they have 5 degrees of freedom. So they have an accelerometer in them. And so you can measure basically not only the vertical motion of the buoy, but also the pitch, roll, and yaw of the buoy, and basically then calculate directional moments, which are representative, for example, of the mean wave direction, or representative of the mean, the standard deviation of the wave directional distribution. And so we can then compare those directly with these results and basically figure out what the directional sensitivity of our instrument on the seafloor is relative to a directional sensor at the surface. Now, interesting things, if we just look at this data, which is most of what I've done over the past few months, there's all sorts of bizarre things. One of them is that there seems to be an entire population of waves that don't belong, and I don't know what they are. If you look, for example, here, you can see, again, with the same plot, it's wave number and then frequency and then a log scale, just to condense things a bit. You can see we have all this wave energy like we expect. It's mostly coming from one direction, but has some finite width. That's the average over 10 minutes. If we look at the next 10 minutes, there's a very large wave or something that's definitely in the right band of frequencies to be an ocean wave. And it definitely is kind of roughly in the right band of velocities to be an ocean wave. But it's coming from the opposite direction. Surprise. So it's like a freak wave or something, even though the amplitude might not be large enough to be formally classified that way. At least directionally, it's very, very far out of the kind of statistical distribution of ordinary waves. And similarly, if we go back here, you can see that with the apparent velocity changing as you go from increasingly oblique azimuth, we expect to see the whole dispersion relation shift up. Whereas you see that this one has the opposite pattern, that it matches the dispersion relation at high frequency and not low frequency. So it seems to also be following a different dispersion relation, and therefore maybe a different sort of wave, like an internal gravity wave or something. If it's not a surface gravity wave, it might be nonlinear. All sorts of interesting things to explore there. But what is interesting is that if you look over here, this is the power spectrum over the 10 minutes, the complete directionally average spectrum, and you'd never see it, right? You'd never see going between these two that there's a statistically very, very different in terms of wave direction, wave coming across the cable. So these will be very exciting to explore in detail. There's definitely multiple per day. So I need to find out a way to kind of automatically detect them, and then we can compare them with like current speed and wave conditions and stuff like that. Another thing is that when the wind is blowing really hard, we get really clear evidence of nonlinear wave-wave interaction. You can see in the raw spectrum that at this particular time, we have our normal wind wave spectrum here, and then there's all these higher harmonics, which are exactly 2 times, 3 times, 4 times the main peak in the spectrum. And what this typically is interpreted to represent, it's been seen in bottom pressure data before in oceanography, is that these waves are basically exchanging energy among each other, resonating like a nonlinear harmonic oscillator or coupled harmonic system of coupled harmonic oscillators. So that'll be very exciting to explore too in more detail. All of this data I'm showing you is from June, and the wave conditions were super, super calm in June. More lately, we've seen wave conditions that are as much as 5 times larger than what was on this day. So I'm very excited to see how this sort of nonlinear modulation evolves with the really, really different sea states. Another thing, since I'm just listing things we can do with this data, we can do is cross-correlate the ocean waves. We were kind of unsuccessful in recovering ambient seismic noise, but the ocean waves are coherent in space. So we can apply the same cross-correlation, particularly on the south cable, because the waves tend to be propagating along the south cable. On the east-west cable, this does not work very well because the waves are more or less 90 degrees oblique to the cable all the time, and therefore our sensitivity to them is a bit lower. And also, we don't really have any what you'd call an interferometric stationary phase contribution, giving us the true phase velocity. But using this information, we can then measure the dispersion relation of the ocean waves and see how it varies as a function of time. Something which you can't do with the unorganized random wave field, at least not as easily. And so what we see here on a very, very shallow water channel, first of all, we have lots of time where there's no measurement. This is because over the course of 3 days here, 1.5 days, and then as a function of frequency throughout the wave bands, this is a part of the cable where the tide is drawn completely out. There's no longer water on top of the cable for certain hours, sometimes a day. Here's one as the cable is coming down the slope, close to, but not yet in that deep channel coming out of Patchmack Bay. And here's one in the deep channel coming out of Patchmack Bay where we know there'd be strong tidal currents. And what we're seeing here on the color bar is the phase velocity of the ocean waves. Again, the vertical axis is a function of frequency. And so what you can see is one, when it's in deeper water further out, the ocean waves are faster. That's known. But what you can see is that not only are the frequencies over which we can make this measurement modulating, but the velocities are modulating quite a lot. If you look, for example, here at exactly 10 seconds, it goes up and down by more than 3 meters per second every 12 hours. And so we can fit this. This is a synthetic model that's fitting this data using just simple nonlinear least squares because it's a nonlinear dispersion relation. And what we can recover are not super robustly variations in water depth as a function of time, but in particular, we can get an estimate of the along cable as well. And what this shows isn't surprising. It basically is as the waves are propagating into a current against it, they're slowed down by as many as multiple meters per second. And when they're propagating with the current, they're accelerated, just kind of like a Doppler shift, like people are probably familiar with. So we can recover that by fitting the dispersion relation and get an estimate of the flow all along the cable. What we can see again is not surprising that channel 6000 is deep in the tidal channel coming out of Patchmack Bay shows an even stronger current than what we observe at the wave buoy in the shallower water. So that'll be fun to do more systematically. So, okay, I've talked about earthquakes and seismic ambient noise. I've talked about oceanography. We haven't seen any sea ice yet. Hopefully we will see some soon in January through March when it's typically kind of peak. What about acoustics? So we're a little bit hampered in the sense that this data is very large and very remote. And so even though we have a small edge computing server there and we can look at it, we have not really done a systematic search through the kind of acoustic band, as I'd call it, which is basically everything higher than what I've talked about before. We recorded for a couple of months all the way up to 250 hertz. And here's an example of this of the spatial spectrogram, the spectrum of every channel of the first 50 kilometers of one of the cables, up to the Nyquist, more or less, of 125 hertz. And what you can see here is an example of a really obvious ship passing over the cable. There's lots and lots of commercial shipping traffic, not only because Homer, Alaska is a big cruise ship port and also a fishing port, but then of course you get into Anchorage, which is a gigantic port much further up the bay. And in order to get there, they have to cross our cables. And so you can see all these beautiful harmonics associated with presumably ship engine lines. This band down here is the ocean waves we were looking at before. If we look at lower frequencies, again, kind of stymied by the Nyquist, we've only pulled out the 2.5 hertz data and brought it back to UW. There's also a very interesting, super spatially coherent, super temporally coherent noise that occurs kind of in the ballpark of half a hertz to a few hertz. And then it goes off of where we can see above 2.5 hertz, because that's the limit of the data we have back here. And I don't really know what this is, but it'll be very exciting to look at. It could be related to like Schultz wave resonances. You have soft sediment, amplified surface waves causes trapping of energy in these interface waves that propagate along the seafloor. It could be acoustic modes of the water column. It's kind of in the ballpark of the right frequencies for the acoustic normal modes of the water column. And it can also be wind-driven noise. But what's most interesting about it is how incredibly spatially and temporally variable it is, which to me suggests that it's probably controlled by the wind. In particular, I've just kind of stepped through like some movie frames. If we look, each of these frames is 10 minutes, right? You can see this strongly dispersive in frequency, right? But also dispersive in space peak that's propagating along our cable at about 1 meter per second. So my best guess is that this is somehow related to individual wind gusts propagating down the cable. I'm just going back and forth. But then we also can see that some of these peaks at higher frequency are more or less stationary. So this will be an exciting thing to, in addition to searching for more ships and marine mammals and all sorts of things that we can do, and we have the higher frequency data, as soon as we can see where these go when they go up above Nyquist, we'll be able to have a more complete picture of what these really are, because it's a pretty exciting kind of interesting signal that I've definitely never seen before. Where's the end? So just as a kind of giant summary of where we are, with a single system, we're recording a year of data across nearly 170 kilometers of telecom cable offshore in Alaska's Cook Inlet. There's lots and lots and lots of earthquakes on kind of on the order of 10 per day that we can actually detect. And so people like Chimin and Yu are developing machine learning codes that will allow us to do things like automatically pick phases and associate phases, and therefore, getting from having this giant pile of beautiful raw data to being able to do tomography and source studies. There's also very clear converted and reflected phases in many events that are somewhat diverse, but are particularly strong for deep events. And so there's potential for interesting waveform modeling, maybe even like reflection imaging using those depending on what they are. Interestingly, that we can very rarely see the P wave, direct P wave, unless it's a very large event or a very local event. That's not too surprising because of the polarization dependent sensitivity. But the fact that the S wave is so coherent, even for really, really tiny, really deep events, suggests that there's a lot of potential for source studies with this data set. On the second point, we didn't successfully observe ambient noise yet. Maybe now that we have 5 times higher ocean waves, there will be significant ambient noise, and we can go take a look. But we were really hoping to see that kind of 1 Hertz local ambient noise peak. But in the absence of that, we're using earthquake coda wave cross correlations to develop this shallow shear wave velocity model, from which we can do hazard-related studies. From the ocean wave data, we can pretty reliably estimate ocean wave point statistics at the sea surface using empirical correlation between the wave buoy and the DAS data, working towards getting directional statistics utilizing our processing. And these really cool observations we have of freak-like waves or rogue-like waves, strong wave current interaction, and some evidence of potential nonlinearity are exciting directions for future research. We haven't found any marine mammals yet, but also we've barely looked for them because we don't have the high frequency data here. But there's definitely some sorts of interesting transient localized noise sources. So I'll leave it there. And I definitely want to, this is as much an overview of what our current ongoing research is an advertisement, because I think that, getting through this data is going to take many years and a lot of hard coding work. And if people have ideas for things to do or tools that they think would be helpful, definitely let us know, because there's a lot of people. I'll go back to the front page who are take a while, who are working on it, but I think that it's gonna, I would guess it might take 5+ years for us to exhaust the possibility of this data, maybe longer than that. Yep, I'll take questions. That's the end. Oh my gosh. Okay, Joan? Yes, please. Right. I don't know. I mean, maybe William probably knows better than I do, but I assume Alaska's had a lot of infrastructure projects that money has kind of come from political reasons, like the roads that they've built out to remote native communities and like near Nome and things like that are like federally funded infrastructure projects. So I have no idea who's paying them. Is it just a business opportunity, or is it some Lisa Murkowski special? I don't does anybody know?
I did summer work in Alaska and whenever we were driving down the road, the potholes, oh, better call Uncle Ted. Right. This is better call Uncle Ted. So it comes in bursts. Like
Okay.
Like sort of in years, that big federal stuff that you build. We're in the middle of mountains, right? The infrastructure, a lot of fibers being built. Like there's a new cable that's being laid along through Darrington. Actually goes right by that bump that says this too happens. You probably will take that's from over the middle mile. That's just again. But I'm guessing that 20 years ago there was much money built cable. It was access that was built for cable. Well, people
Well, yeah, the Cook
going to be on radio.
Yes.
We'll put that 1%.
But the, Unalaska connection and the people up at Quintillion who connected the North Slope to Nome by going all the way around, I don't. I- where does the money come? Yeah, but it's it's expensive. Where does the money come from? Good question. They didn't care. I mean, so we checked. William contacted the folks at the APO who are kind of our liaison for the Navy, and we emailed them and asked because they had an interest in particularly the OI experiment offshore Central Oregon. They wanted to take the data, approve it as being submarine free or whatever they're looking for, and then give it back to us. And they didn't seem to have any interest in this. So I guess they don't. I mean, it's very shallow water. Maybe they just don't drive anything of significance into the Cook Inlet. Please. The ocean signal dominates, which I would say is fortunate, but you need to have something in the data. I think there's no evidence of tremor so far. Particularly, let me find one of these spectrum plots. You can see here, right? The tremor would be in this band and higher off the top of the screen, right? It would be kind of 1 or slightly less than 1 hertz, at least kind of eventually detected. Because there's this really strong regional microseismic peak, this is the seismometer spectrum. I actually have wondered whether the detection of tremor that just stops at Anchorage is because suddenly there's microseism and the local stations can't see the tremor because it's overprinted by the wave energy from Cook Inlet, but it should still be there. I don't know. I don't have any good evidence of that other than that there's other signals in that same band. We don't see anything up to 1 hertz in our data. It's all ocean wave energy. And then the ocean wave energy dies off, but the instrumental noise is too quiet. I think the instrumental noise is basically set. But you can see in this band, this is the DAS data. Basically, the cutoff of the ocean wave energy, which is exponentially with depth, is here, around 0.3 hertz. But then above it, you can see that the tidal modulation of the ocean wave energy is still affecting the noise level of the instrument. And I suspect that it's just some nonlinear mechanism for optics, like, for example, the fact that it's doing phase unwrapping and things like that. There's some error rate that's dictated by the amplitude of the maximum signal. Because it seems like the instrumental noise, which is all we see in that band, ordinarily when there's not an earthquake, is somehow still dependent on the ocean wave energy. It's so similarly at low frequencies. But also, I can't say anything definitively because I have almost exclusively looked at data with a Nyquist of 1.25 hertz. And so, there could be many more interesting signals between 1 and 10 hertz that we just haven't had an opportunity to see it. Right. So that's a total next step. I think Zoe was interested in potentially looking for that. Because what I did simply there, I know I did not do a great job explaining this. I didn't want to get too granular, is take the average transfer function over a month, right? And just use one time invariant transfer function to basically convert the DAS data into the wave buoy data. So that we could then do the same thing for other months, for example, right? And so what it's probably means is that basically when the wave energy, because the compliance related signal induced by the ocean wave loading is vertically polarized, it's basically like a quasi-static Rayleigh wave. I think that when the ocean waves are propagating closer to parallel to the cable, we see a larger signal just because the particle motion projected into the cable axis is larger. And the fact that there's a lot of directionally spread out ocean wave energy, it's going in a lot of different directions once, means that this doesn't totally kill our measurement. We can use a directionally invariant transfer function to kind of get the average right, because the ocean wave directional distribution is large, but or is wide. But there's no way to basically separate the fact that there's a different directional component of straining projected into the cable direction when the waves are 30 degrees different from each other. So I think a vector version of that simple equation will fix the problem. At least I hope so.
Well, let's pause there and thank Ethan for his presentation.